electronegativity and bond polarity. Okay, so the Lewis model, really nice and simple with the little dots, but this is a drastic oversimplification of what's going on. Still really useful, though. The truth is those electrons are not always shared equally. Okay, just like if you've got the 12-year-old brother sharing a cookie, with a 5-year-old brother, or maybe even younger, like 3, right? You break the cookie in half, right? Oh, I gave him half. Yeah, you gave him the really little half, right? They shared, but it wasn't equal. When atoms share electrons, it's not always equal either. So if we look at hydrogen and fluorine sharing an electron to make a bond and form hydrogen fluoride, what happens is that the fluorine is much more attractive to the electrons than the hydrogen is. And so these electrons are going to be pulled over to the fluorine. You're kind of like hogging the blankets when you're sleeping in bed with someone. They're always taking the blankets, right? So this fluorine is hogging the electrons. And so this end of the bond becomes more negative because there's more negative charge over there, and this end becomes more positive. Here's an illustration showing electron density. And so it bulges out over here because the electrons in this bond are spending more time around the fluorine than they are around the hydrogen. So we can indicate that with this. This is the lowercase Greek letter delta. It's like a D with really bad posture. So delta plus and delta minus. This is not an ionic compound. Hydrogen fluoride, as a pure substance, is not ionic. It's molecular. It's a covalent bond. But it's a very unequal covalent bond. So the hydrogen end is partially positive. Not +1, but maybe +1/3 or +1/5, a little bit. And this side is negative a little bit. We don't care exactly how much it is. We just care that one end is a little bit positive, one end's a little bit negative. And we can observe this using experiments like this, where you have these 2 charged metal, or in this case over here, they're not charged, 2 metal plates, and the hydrogen fluoride molecules are just going to be floating around. And they're going to have random orientations. And then you put a charge on the plates. This one's negative, this one's positive. The positive charge attracts the negative end of the molecule, and the negative charge attracts the positive end, and all of these are going to spin like little compasses, and they're all going to line up. And then it actually happens. So we call this a polar covalent bond. What's different about the North Pole and the South Pole of our planet? Opposite magnetic fields, right? A compass is a little almost frictionless spinner, and it's made out of metal, and it can line up with the magnetic field, and so it points to the North Pole. So poles, you've heard the word, the term polar opposites, right? So these 2 things are very different. Polar covalent bond, the electrons are being shared. That's what covalent means, sharing of valence electrons. Polar means there's a difference. One end is different from the other. So we've got unequal sharing. Another way we can indicate this on a bond is through this arrow. The arrow points at the one that's more electronegative or more attractive to the electrons, and the positive is on the positive end. So I have an analogy for this one involving little electrons as little boys. So hydrogen is one house, and fluorine is the house next door. And each of these has an electron, a little boy, and the little boys are playing together. And so that's this single bond. A pair of electrons are playing together. At hydrogen's house, they don't have cable, and they've got an old VCR and some Thomas the Tank Engine videos. And these kids are like 10. And if you're hungry, Mom will give you saltine crackers and water from the tap. Not even ice. Good grief, right? So just not a whole lot going on over there. And over here, they've got every channel known to man. They've got a television screen the size of the wall. They've got a trampoline and a swimming pool in the backyard. And if you're hungry, Mom will order pizza. They have a soda fountain in the kitchen. Where are those two little boys going to spend more time? At fluorine's house. It's more attractive, right? So they are going to come over to hydrogen's house a little bit, but they're going to spend most of their time over here. It's not a transfer. It's not an ionic bond. An ionic bond would be that hydrogen signed off on her rights to her child and let fluorine adopt him, right? And now he belongs to fluorine. This is still sharing. He still lives there. That's still his mom. And I see this arrow as, somebody comes over and wants to know where the kids are. Dad's out in the front yard mowing the lawn or something, and he's pointing. They're over there. So the arrow's pointing to the more attractive to electrons side. So how attractive something is for electrons is called electronegativity. The ability of an atom to attract electrons to itself in a chemical bond. We only talk about electronegativity in chemical bonds. It is inversely related to atomic size. And that has to do with that distance, right, and the attraction that we saw in the bond lengths for the, or the lattice energies for the ionic compounds. This is kind of the same idea. So fluorine is the most electronegative element. The noble gases just don't really make bonds, and so we just completely leave them out of any discussion of electronegativity trends. So here's a cool graph showing electronegativities of different elements. So you'll notice that period 8 is not on here because they don't form compounds, so we cut them off. Excuse me. So there is a general trend as you're going from left to right that it increases. That's opposite to the trend in size, right? As you go across a period, size decreases. Well, electronegativity is inversely related to size. So you go across, it increases. And in a group, as you're coming down, atoms getting bigger, electronegativity is getting smaller. The way I remember this, fluorine's up here in the corner. Fluorine is the most electronegative. It's the awesomest place for those little boys to be. The closer you are to fluorine, the more electronegative you are. Okay? The farther away, the less electronegative. Those are trends, not absolutes. You'll notice hydrogen, got to be an exception to everything, right? He's more electronegative than beryllium. Sorry, it just is. These are the actual numbers. So this scale, it was an arbitrary scale. It's relative. So they said, well, fluorine is the most electronegative. We'll call that a 4. And 0 would be no attraction for electrons. Well, none of them are 0, but there's a range. You do not need to memorize actual electronegativity values, but you do need to know the trend. Fluorine's the most electronegative. Any questions? So bond polarity. So a polar bond is unequal sharing. A nonpolar bond is where the sharing is perfect. It's equal. Well, of course, like many things, there's not really a hard and fast line. And so we kind of had to make a line. It's actually a continuum. And so the degree of bond polarity is going to depend on the difference in electronegativity. Electronegativity is a long word, so we often abbreviate it EN. So the difference in electronegativity between those two atoms. So here we have an example. Here we've got a yellow and a yellow. Those are the same element. They're going to have the same electronegativity, right? They're going to share equally. So this is going to be a nonpolar bond. So that would be a difference of 0. And we'll say if there's a small difference up to 0.4, we're still going to call that nonpolar. At the other extreme, you have ionic bonds, where the difference is so great that the electron actually leaves the one atom and goes and permanently moves into the other atom's house. Right? That's an ionic bond, a transfer of electrons. And we call something ionic if the difference in electronegativity is 2.0 or greater. And then in between here, we have polar covalent bonds with unequal sharing. I'm not going to make you memorize that 2 and 0.4 are the dividing lines. You might need to look that up for some homework problems. What I want you to be able to do is, using the periodic table, predict whether the bond is polar or not. So my rules, I probably don't have them in here. My rule is that it's nonpolar if it's the same elements, same element. So you look at those two atoms. Same element, nonpolar. It's going to be ionic if you have a metal and a nonmetal. Metal and nonmetal. And it'll be a polar covalent bond most of the time if it's two different nonmetals. Now that's not always, but most is pretty good, right? And it's going to be good enough for my exams. Okay. So you can quantify this amount of polarity. Dipole moment is a measure of bond polarity. It's given the symbol mu. Dipole moment occurs anytime there's a separation of positive and negative charge. So the dipole moment is equal to Q, where Q is the charge magnitude and R is the distance between them. So the farther they're separated, or the higher the charge, the greater the dipole moment. Dipole moment has a weird unit, the dBi. This is different than Dubai, cool city. This is dBi, and it's actually a Coulomb meter. Coulomb is a unit of charge, meter is a unit of distance. So I'm not going to test you on that. If we look here, we see difference in electronegativity. A chlorine molecule, two chlorine atoms, same electronegativity. They're the same element. Difference in electronegativity is 0. The dipole moment's also 0. If we get to like lithium fluoride, where we have a metal and a nonmetal, we have a high difference in electronegativity, and we have a large dipole moment. So the higher the dipole moment, the more polar the thing is. Ionic is just extreme polar. Any questions? We could also look at percent ionic character. That is the ratio of the bond's actual dipole moment to the dipole moment it would have if the electron was completely transferred. And what I would like you to get out of this is that no bond is actually 100% ionic. It's convenient for us to think of that, but it's not actually the case. So if we graph percent ionic character versus difference in electronegativity, we see these clusters. And that's why they decided to, well, if the electronegativity difference is greater than 2, it's an ionic compound. So when we get over here to 2, we see that all of these guys have very high percent ionic character. It's considered ionic if we have 50% ionic character or greater. And these are all metals and nonmetals, aren't they? Except here's HF. He is very close on both scales to being ionic, but he's not. And over here, with less than 25% ionic character and electronegativity difference less than 1, these guys are going to be polar, but they're definitely not ionic. Any questions?
So the electronegativity must be greater than 2 and 2% ionic.
So the guideline, it's two different methods for identifying. This graph is showing that they coincide for the most part. So you can look at difference in electronegativity and say, well, if it's more than 2, then it's going to be ionic. Or you could look at percent ionic character. You wouldn't look at both necessarily. And so, you know, it's really great that we can quantify this and everything. For our purposes, we just want to be able to identify, is it ionic, is it polar covalent, or is it nonpolar covalent? And the guidelines I gave you over here will work for that. Nonpolar if it's the same element, ionic if it's a metal and a nonmetal. Your best guess is polar if it's two different nonmetals. That will be wrong occasionally, but not enough to make much of a difference. Okay, so this is the kind of thing we should be able to do. Determine whether the bond formed between each pair of atoms is pure covalent, polar covalent, or ionic. Your book uses this term pure covalent. I prefer nonpolar. Nonpolar covalent. So a bond between iodine and iodine, what's that going to be? It's going to be nonpolar. How about between cesium and bromine? Ionic. Cesium is a metal and bromine is a nonmetal. So that's going to be an ionic. And we would name it as an ionic compound. How about phosphorus and oxygen? Two nonmetals, we're going to predict that that's polar. Okay? So let's just go back and double check on our table here. So here's phosphorus, 2.1, oxygen's 3.5. Yeah, that difference is greater than our guideline of 0.4. You can have bonds between two different nonmetals that are nonpolar. So carbon and sulfur both have electronegativities of 2.5. So a carbon-sulfur bond would be considered nonpolar. I don't think you need to remember that. The only one I'd like you to remember is that a carbon-hydrogen bond is considered nonpolar. Carbon's 2.5, hydrogen's 2.1. It's right on the edge there, but carbon-hydrogen bonds are extremely common. These other bonds, not so much, but a carbon-hydrogen bond is nonpolar. Didn't mean to do that. So carbon-hydrogen is considered nonpolar because the difference, delta En, is 0.4.